Hi there, Mr. Sutton here, bringing you the Algebra 2 10-2 lesson on angles and radian measure. In this one, we will learn how to draw angles in standard position and find coterminal angles. We will also be converting between degrees and radians measures of angles. And for the honors portion of the course, we'll be finding arc length and areas of sectors. We're going to start this lesson off by getting the lay of the land with some definitions, the most important of which is what is an angle. So we dealt with angles already with triangles, and you're thinking, okay, an angle is like a V sort of shape where two rays come together at a vertex, and that's all very cool. Another way we can think of an angle that'll be relevant to what we're doing today is we can think of an angle as an amount of rotation. And we can use this little theta symbol to stand for an unknown angle like we've been doing. So if we're talking about rotation, we probably want to have a circle to visualize all this. Now, these angles that we're talking about, they do have two rays coming together at a vertex. The vertex is going to be at the origin of this circle, and the two rays have special names. One of them is the initial ray. This is the one that's fixed on the positive x-axis. And if we're talking about x-axis, we should probably label it. So here's the x-axis, and here is the y-axis. And this initial ray is fixed on this positive part of the x-axis. Now, there's another ray called the terminal ray. This is another ray that is allowed to rotate freely to describe whatever angle that we want. So let's rotate this just once, just to see it in action. There we go. So however much this rotates away from the initial ray, that is your angle. Now, one other thing we want to be aware of visually is that the x and the y-axis are chopping the circle and really the whole plane here into four quadrants. Since we have a circle, that means there's 360 degrees to go all the way around this. So that means each of these quadrants is 1/4 of that, or 90 degrees. So that means we have four 90-degree quadrants. And they have names or numbers, usually using Roman numerals. So quadrant 1 is right here. And then we've got quadrant 2 in the upper left, quadrant 3 in the lower left, and then quadrant 4 in the lower right. And although we're using Roman numerals, you could use normal numbers. It doesn't really matter. Now, between these quadrants are some angles. And those are called the quadrantal angles. These are the angles that are not in any quadrant. They actually are the kind of the border angles between the quadrants. And just while we're labeling these, it also is helpful to know that our positive angles are going to spin in a counterclockwise, lefty-loosey kind of direction. So 0 degrees is right here at 3 o'clock. And as we go counterclockwise, this up here is 90 degrees. I mean, you can see the right angle in there. And then another 90 brings us to 180. And then we're down here at 270, separating quadrants 3 and 4. And we could come back here to 0, but we're going to call it something else when we do, and we'll get there in a minute. While we're talking about positive angles, though, spinning counterclockwise, you might wonder, hey, what happens with negative angles? You can have those too. Negative angles just spin clockwise. So if you started at 0 and you went clockwise 90, we could call this value down here negative 90 degrees instead of 270 degrees. So it's just another way of thinking about the same position. Now, since these are essentially the same position, but we kind of took a different route to get there, we actually have a concept for this. These are called coterminal angles because the terminal ray would be facing the same direction for each of these angles. Coterminal angles are basically the same position like these two here, but numerically they're either 360 or some multiple of 360 degrees apart. It's basically you got to the same place, but you did it by either spinning a different direction or by going around the circle multiple times. And each time you go around the circle, you're either adding or subtracting another 360 degrees to your angle. Speaking of which, if we started at 0 and went counterclockwise all the way around, we could also call 0 degrees 360 degrees. And there's an infinite number of these coterminal angles for any of these. 90 we could call, negative 270 or 450. We could go as long as we want. 360 is a good one to remember, though. Now, because we have all these infinite number of angles, it's good to have sort of like a base case sort of angle that we can, say what the angle is, and we have a good idea of where it is on this circle. So we have this concept of a standard position for angles. If I ask for the standard position, I'm just asking for the version of the angle that is between 0 and 360 degrees. So the thing that would go on the normal version of this circle. And notice here that 0 is included, but 360 is not. 360 just misses the cutoff for being a standard position angle because 0 already took that spot. Now, if you start with an angle that's not in standard position and you want to turn it into one of these to make it a little easier to work with, it's pretty simple. You just have to convert angles to standard position, you just have to keep adding or subtracting 360 degrees until you get an angle that's between 0 and 360. Now that we've had that intro on all things angles, let's get a little practice drawing angles in standard position. So I've given you 3 of them here, 240, 500, and -50. They each have their own little challenges kind of built into them. Here are some places you can draw the angles on. So pause the video and see if you can draw these, and keep in mind you might have to alter the number a little bit to standard form, standard position, before you can fit it on our standard 0 to 360 sort of scale. All right, let's see how that went. So 240 is already between 0 and 360, so I don't have to do anything to it numerically. And it's between 180 and 270 specifically. And it's going to be a little closer to 270. So this angle right here would be 240 degrees. Coming over here to 500, that's bigger than 360. So to get on this standard range here, I want to subtract 360 from that. 500 minus 360 is going to give us 140 degrees. So 140 is somewhere here in quadrant 2, maybe a little bit closer to 180, but not by much. And then finally we have -50. That's less than 0, so again it's outside of our standard range. To get it in the 0 to 360 range, we're going to add 360 this time around. So -50 plus 360 gives us an angle of 310 degrees. And 310 is somewhere around here. So we've seen we can use this 360 idea and coterminal angles to get something in standard position, but what if we just want to get a coterminal angle just for its own sake? So here's a problem like that. They want us to find one positive and one negative angle that are coterminal with -45 degrees. So pause the video and see if you can come up with 2 angles that match these descriptions. All right, if I want a positive angle and I'm starting with a negative, I need to add 360 to that. -45 plus 360 gives me a coterminal angle of 315 degrees. And if I want a negative angle, the only way I can get that is if I subtract 360 from -45, and that's going to give me -405 degrees. So up to this point, we've been doing everything with degrees for our angles, but it turns out angles can be measured in either degrees or something else called radians. So let's talk about these 2 different ways of measuring angles. So degrees we already know a little bit about. It's kind of hard to define what a degree actually is, but we know that there's 360 of them in a circle. So if I had to kind of pinpoint what is a degree, well, a degree is kind of like 1/360th of the way around a circle. However far that is, there's 360 steps you take to get around a circle. Now, have you ever wondered why it is 360 and not, say, 100 or 10 or something else like that? Well, there's a lot of stories about this. The one I keep hearing, though, is that the Babylonians came up with 360 because they had a base 60 number system, and because there's almost 360 days in a year, so it was kind of a convenient number for them to use, and it just kind of stuck around. In any case, it is a little bit arbitrary. The radians is less arbitrary. If you ask me what a radian is, I can tell you precisely. You might notice the word, it has the word almost like a radius going on there, and that's for a reason. A radian is actually equal to the length of a circle's radius. It's still a way of measuring sort of distance or spin around a circle, but we can actually pin down what they're talking about here. So 1 radian would be if you took this radius here and sort of bent it around the circle, however far that took you, that length would be a radian. So that's the basic concept. Let's talk about how we can switch back and forth between radians and degrees. So if we think about a radian as radius length, well, the easiest one to do would be if you have 0 degrees, if your terminal ray is at 0, so that you have 0 spin. That means you have 0 radiuses going on, 0 radii. So 0 degrees and 0 radians are actually the same thing. But how many radians would it be to get all the way around a circle? Well, all the way around a circle is called the circumference, and we have a formula for circumference. You might remember C equals 2 pi r from your geometry days. Well, that means it takes 2 pi radiuses to get around a circle. 2 pi is roughly, it's like 2 times 3.14. So it's like a little bit more than 6 of these radiuses. If you bent them here, they would get you all the way around the circle. Well, all the way around the circle is also 360 degrees. So that means that 2 pi radians and 360 degrees are actually equivalent to each other. So we can, in addition to this little 0 here, I can also write a little 2 pi next to the 360. And you can use the circle that we worked on earlier when we were talking about just the basics of angles. Okay, so how about some of these in-between angles? Well, to get halfway around the circle to 180 degrees, I have to take half of 2 pi. So that would just be 1 pi. So we see that 1 pi radians is equal to 180 degrees. And it turns out this is going to be the key here to unlocking pretty much any conversion we want to do. But for now, let's just put a pi right here. And I can get a few more of these almost for free. 90 degrees is between 0 and 1 pi, so that's half a pi radians, or pi over 2. And 270 is halfway between 1 pi and 2 pi, so that's like 1.5 pi or 3/2 pi, or you will most likely see it written as 3 pi over 2. And there's a few others that we can write here, but I think that gets you the basic idea. Now, one thing you might notice before we talk about getting even more of these radians is that I didn't write the word radians next to any of the things I put on here. And there's a reason for that. Typically, the convention is not to write radians. Just leave no units at all. We understand that if there are no units, that really means radians. And if we have degrees, that means degrees. So that's really the only way you're going to have to tell the difference between degrees and radians. Is there a degree symbol or not? So this means that when you're supposed to find an angle and write it down, make sure you write a degree symbol if it's really in degrees, because if you don't, it means something totally different. Okay, so how can we get some of these other angles that aren't so easy to pick out because they're halfway between things? Well, this pi radians and 180 degrees equivalence is going to help us out here. To convert from degrees to radians, we're actually going to multiply whatever your degrees is by a conversion fraction that has pi and 180 degrees in it. Specifically, we're going to multiply by pi over 180 degrees. What this is going to do, if you have degrees over here being multiplied by this, is the degrees are going to cancel out, and this invisible radians unit is going to be all that's left. Now, the good news is to go back and convert from radians to degrees, we just have to reverse this process. And that would mean dividing by pi over 180 degrees. But we don't like to divide by fractions, so instead we're going to multiply by the reciprocal of this and multiply by 180 degrees over pi. This would cancel out the invisible radians unit, and then you would have degrees left over. So in a moment, I'm going to have you try out these two problems here, where you have to convert back and forth between degrees and radians. Before we do that, though, because you might be thinking, well, I just need to multiply by some fraction with a pi and a 180 in it. How hard can that be? The trick is we typically ask folks to do this without the use of a calculator. And there's a lot of other no calculator things that are coming up in this chapter, but this is the first big one. So in order to be able to do this completely without a calculator, to make reducing with 180 easier, because you're going to have a lot of fractions with 180 in them, it helps to learn some factorizations of 180, some common ones. So we'll just go through them one at a time. So we've got 1 times 180. 2 times 90. Feel free to pause the video and see if you can come up with the rest of them. All right, so we have 3 times 60, and then 4 times 45, 5 times 36, a lot of people forget that one, 6 times 30, and let me see, 7 and 8 don't work, 9 works, 9 times 20, 10 times 18 was pretty easy, and then there's one that a lot of people forget about, but every now and then we need it. That would be 12 times 15. So these are the big ones. Probably the 1 and the 180 doesn't get used a whole lot, but these other ones get used quite a bit. So it helps to be able to divide 180 by one of these numbers and know that the other number is waiting for you. And also one piece of advice I'm going to have, and then I'll set you loose on these problems. It's a good idea to cross-reduce whenever possible before you multiply straight across with your fractions. You're going to see some big numbers if you don't do cross-reducing in advance. So with all of that said, pause the video and see if you can convert each of these things to the other type of measurement. All right, let's do the 120 degrees first. Since I want to get rid of degrees and get radians, I need the radians on top of my fraction and the degrees on the bottom. So I'm going to be doing pi radians over 180 degrees. And again, we can cross-reduce on a lot of these. 120 and 180. Those are both reducible by 60 is the biggest number, but you could reduce in parts if you had to. So if I reduce these both by 60, this is going to be a 2 up here and a 3 down here. So multiplying across now, that leaves me with 2 pi over 3. Now let's do this other one, negative pi over 12. We need to convert this to degrees. So that means now I need the degrees on top and the pi radians on the bottom. So we've got 180 over pi there. Now 180, now first off these pi's cancel, so that's good. But also the 180 and the 12 are reducible. We see up here that 12 and 15 gets us 180. So if I reduce that, that leaves me with a 15 up here. Awfully convenient. So this is going to be a negative 15 degrees. Now one thing that is important to note is that, again, the only way we know if it's degrees or radians is whether we see the degree symbol. If you see numbers that do not have a degree symbol and do not have a pi in them, those would be radians. It doesn't have to have a pi to count as radians. It just has to not have the degree symbol. If you are taking the CP non-honors version of the course, we've got another problem for you to try out. So you can pause the video and give this one a shot. If you're doing the honors version, just move on to the next problem. We've got something a bit different than this in store for you. All right, let's see how this went if you're doing these problems. So this first one, we need to convert it to degrees. So let me multiply by 180 degrees over pi. Pi's cancel. 180 and 3, that can reduce to 60. So we have 7 times 60, which is 420 degrees. Next, let's take a look at converting 160 degrees into radians. So now we'll multiply by pi over 180 degrees. The degrees cancel, 160 and 180. Those can reduce by 20. That's the best number. So that leaves us with an 8 up here and a 9 down here. So that ends up being 8 pi over 9. And this brings us to the end of our lesson if you're taking the non-honors CP version of the course. Feel free to turn the video off and try some conversion on the homework. And have a good one. Till next time, Mr. Sutton signing off for you folks. So for the last question in the honors part of this lesson, we have a softball field here that they say forms a sector, whatever that means, with the dimensions shown here. So we've got 200 feet from home base along the out-of-bounds path to the outfield here. And that is pretty close to what I've seen in terms of standard lengths. They want us to find the length of this outfield fence here and also the area of the field. And then they said we can leave pi in the answer, so we could theoretically then do this without a calculator is what that's really saying. So what does this all mean? So we need to tell a little bit of a story before we can get to this. And that story begins with a circle and something called a central angle. A central angle is a angle whose vertex is the center of a circle. So we can draw some kind of angle based off of that, and we've got our little theta in there to represent whatever that angle is. And we also know that the legs of that angle then are going to be the radii of the circle. So when we create this central angle, we're essentially slicing our circle into a piece of pie almost, like pie that you would eat. That slice that's created by the central angle, that is what we are calling a sector. That's a slice of the circle. And the arc along here is literally called an arc. That's the curved outer edge of the sector. So we have a central angle, we have a sector formed by it, and we have an arc kind of giving us the outer boundary of that sector. So the two big things they're looking for us to figure out in this problem down here is they want to know the area of this slice and also the distance of this outer edge. So the outer edge, let's deal with that one first, because this is kind of what radians are really good at. So this is the arc length is what we're calling this, and we usually use a little s to represent it. So for something that's already has our angle in radians, remember that the radians tells you how many radii you need in order to get from one end of the angle to the other. So this distance is literally just going to be the radians, the angle, theta, times the radius. Theta times r. That is our arc length. So radians almost sets you up for this right away. Now, how about the sector area, which we're going to call A? So we start with kind of the idea of the area of a whole circle. Pi r squared, you might remember from back in the day. But we don't want the whole circle, right? We just want a piece of it. So it turns out if you want to figure out what percentage of the circle you need, you can use the central angle and just divide whatever the central angle is by the 360 degrees, or if you're in radians, you could do your central angle divided by 2 pi. And that would give you the proportion of your circle that you actually needed. Now we can clean this up a little bit. These pi's are going to cancel, and all that's going to be left is we're going to have this 2 in the denominator still, so we're going to have a 1/2. We're going to have this theta, that didn't go anywhere, and we're also going to have this r squared hanging around. So 1/2 theta r squared gives us our sector area. So these two formulas are everything we need to answer the question down here. With these formulas in hand, pause the video and see if you can figure out this problem here. All right, let's do the outfield fence first. That's going to be this arc length formula, theta times r. So in this case, we've got an r value of 200. And then we also have the theta. They gave it as 90 degrees, but we need to use radians for both of these formulas here. That's just the way they're built because of how radians work. So 90, that's a quarter of 360, so that's really 1/4 times 2 pi, so pi over 2 was 90 degrees. So we've then got 200 times pi over 2. 202 can reduce to 100, so that's 100 pi, and that's in feet. Or if you want to do this times like 3.14, we can call this 314 or 314.2, however many digits of pi you want to go. Let's do the area now. So the area of this sector is just using this area formula here. So we've got 1/2, the radius is still 200, and we also have pi over 2 for our angle. So now if we clean this up a bit, and we can do this without a calculator, so 200 squared, that would be 40,000. Half of 40,000 is 20,000, and we have to divide by 2 again to get 10,000. So that's 10,000 pi, and that's in feet squared. Or taking it out a few decimals, 31,416 square feet. And with that done, we have reached the end of this ball game. Until next time, Mr. Sutton signing off.